Okay, same idea as before. This time we're going to do a little more algebra involved instead of just graphing it. Vector and parametric equations of a line. And question 2a says they want us to find the equations of the vector equation and the parametric equation of a vector that passes through this point here, and has a directional vector of m, -3 and 3. So what we're going to do is we're going to refer back to those equations we talked about in the very first place. First equation said our vector form is equal to vector r0 plus t directional vector m. Okay, so we're going to use this idea to plug these points in. So what we're going to do is our vector r0 essentially is 1, 4. This is our point on our vector. And some parameter or scalar of directional vector 3m. Now what this means by this parameter or scalar vector is no matter what I multiply our two component parts by, we're still going to end up in the same direction. We're just going to have maybe a different magnitude or different points along that line. So any value of t will give us any point along this vector. Okay? And it's infinite. There's infinite values of t, which will give us points all along this line here. So that is our vector equation. Okay? We have it in component form. Our components are 1, 4, and it's some scalar for a directional vector of -3 and 3. That is the vector form of the equation. We just simply plugged our values in, our r0 or our point along it, and our directional vector. Now the parametric equation, I constantly say that wrong. Okay. The parametric equation is we're going to be taking our x and y values and setting them equal to our vector equation in the first place. So our x values will be here, okay? And now our x value also needs to be multiplied by our scalar of t, along with our y value eventually, when we go to set an equation equal to y. So parametric equations have, depending on the number of points, whether in 2 space or 3 space, we're going to have either 2 or 3 equations for them. We're going to have an equation that is set equal to x, and we're going to have an equation that is set equal to y. Now our equation that's set equal to x is essentially 1, and then we multiply our t to our x value inside the bracket. So we're going to get subtract 3t. And what that means is we can find our x value, or any x value, with some scalar of t along this vector. And our y, same idea. We're going to take our y value, 4, and we're going to multiply t by our y value of our directional vector again, plus 3t. Okay? And such that they do want us to always write that the parameter is any real number. Okay? As long as it's a real number, we're going to be okay. So that would be the parametric form of the equation. We're going to have to get used to setting up both of these as we go through it. That would be our parametric form. Okay, part B asks us to actually sketch this line. So we're going to do our best to it. I do want to draw your attention to one other thing. We did write this up, okay, after. This also helps with our parametric equation, because think of this as our x value, our x naught value, and our final TA value, okay? We did write that also in the equation. This is how we could set it up easily. I should have wrote this equation in there now that I think of it. Okay. And what that is the parametric equation also tells us that x is equal to x naught plus TA. I don't know why I wrote it like that. And our y naught and TB. Our y would be equal to y naught plus TB, which was in the equations we originally wrote. Okay? And this is a simpler way to just plug it into the parametric form of the equation. Now B says, like I stated, we need to sketch this line, determine the coordinates of 4 points along the line. So they want us to sketch this line here. We're going to bring in graph. We'll zoom in here. Okay. So, if you guys recall, we had our directional vector at -3 and 3. Now, with directional vectors, it's usually easiest, like a fraction or when you're factoring, to put this in lowest form. Is there a number that we could take out of this? Both of these terms, think of it as common factoring. A common term I can take out of both of these numbers. You guys think of one? 3. Okay? So I want you to think of that. Right now we're actually using the scalar 3, or our t-value is 3 when we use this point here. And our directional vector can be considered just -1 and 1. Very simple, easy to write out. -1 and 1. This is going to be our directional vector. Right away we know our vector is going to be on a 45-degree angle. Okay? We're going at -1 and 1. So that helps with our direction. Our point was at 1 and 4. So we go and write our point A, I think they called it. And then from there we can equate our directional vector. So there's a couple ways we can do that. We can follow it. Remember, we know that this is our directional vector, or commonly known when you're in grade 9 as your slope. We can just essentially follow this up. This would be another point. This would be another point. Here and here. Okay. So even though we have point A at 1 and 4, because we know our direction from whatever point we're at is to go -1 in the x direction and +1 in our y-axis, or our y direction, we can do 2 points to the left of it, which will be at 0 and 5, and -1 and 6. Or we could go to the right with the opposite by going to the right one and down 1, and that's going to give us 2 and 3, and 3 and 2. So these would be 4 points along our line. Remember right here. Technically the direction's the other way. Okay. So we have 4 points along our line. We can also try to solve these by making scalars of it by actually plugging in values for t. If we go back to our parametric equation here. Okay. We could have put in different values of t, or scalars of it, and found out these coordinates the same way. If we plugged in a value for t, let's think of an arbitrary one. Say we had -2 for t. No, let's try to find one that'll be along here. If we want x value, or sorry, actually we could also do it the reverse way. We could find out the x values instead of finding the scalars of t. We can plug in values of x and solve for t. And it would also give us, once we have a value of t, we could plug t in and solve for the same value of y. If you guys remember, this is kind of like a table method when you guys were graphing back in grade 9 and 10. So say we wanted to find our x value at 0. Okay, let's jump back up. What's the equation? X was equal to, what did we just say it was? I lost it. 1 and -3. Okay. If our x value is 0, we can move over the -1, -3t. Okay. And we're looking at a parameter of 1/3 for our scale of t. y4 plus 3t, is it? Is that right? Was it negative or positive? It was positive. Good. Okay. So, let's say we're trying to find the x value like we said before. We had our x value in. We solved for our t. We can now plug that same scalar or parameter in for our t of the y. And we know our y coordinate will be 4 plus 3 times 1/3. What's 3 times 1/3? 1. Our y value is at 5, which is exactly what we found when we sketched this graph above. We found our y-intercept to be at 0 and 5 in this question. So there's a couple ways we could have found different points. We could have also gone about it just plugging in any other x values to find other y values along this equation or vector. Okay, and question C actually gives us a good question down here. We'll use these. C asks if point Q at -21 and 23 is on the line, and if point R at -29 and 34 is on the line. Say R? Yeah. -29 and 34. So they want to know if these 2 points are on the line. Well, we could go up to our graph and sketch it, but that could take quite a while. Instead, we're going to use the parametric forms of our equation to solve this. These are x and y naught values, okay? They're looking for just some points along this. So, we're going to use our parametric parts of the equation to solve this question here. Again, we have our x value. We know that x was equal to 1 minus 3t. So we're going to plug in a x value of -21 like we stated before. So -21 is equal to 1 minus 3t. When I move 1 over, we'll get -22 is equal to -3t. And we'll get -22 over -3 equals t, which is essentially the positive version. We'll leave it at that for now. Okay. We're then going to have to solve for our y coordinate. So our y value was y was equal to 4 plus 3t. Is that right? Were they both 3t? Our y value being 23 is equal to 4 plus 3t. When we move 4 over, we're subtracting by 4. We have 19 is equal to 3t. And t in this case is 19 over 3. Is t equivalent between the two equations? No. So what do you think that means in terms of this point being on or not on the line? It's not on the line. In order for it to be on the line, both equations have to hold true. They both have to end up at the same number. Because our parameter or scalar was different when we plug those two numbers into our parametric form of the equation, this point does not lie on the line. Hopefully it does. Let's try the other one and see if it does. Same idea. -29 equals 1 minus 3t. -30 equals -3t. T equals 10. Why it's going so slow? There we go. And 34 equals 4 plus 3t. 30 equals 3t. T equals 10. Does this point lie on the line? Yes. Because both held true and t was equal to 10 in both instances, then this point does show up on our vector or our line.